Thank you. Well, I forgot to put my name there, but it's just my first name and last name together in lowercase at gmail.com. And my Twitter indicator is the same, at Joan Vilaltella. But I don't use Twitter very much. Well, I'm not exactly a computer programmer or software developer. I'm halfway between computer programmer and mathematician with a background in physics. I always work in small scale, and for me it's good to go to talks like this one because I get some consciousness about the complexities of industry-level software, as we have seen just now. And this is a humbling experience, I would say. So I just want to share my joy of discovering some cool Python features. I don't know exactly what the composition of the audience is. If you are very knowledgeable in Python, you may find this talk a little shallow, perhaps. I apologize in advance if this is the case. I will try to show why a mathematician like me can find some of the Python features really cool and useful and conceptually satisfying from a mathematical point of view. And to tell something more about me, I have a background in physics and mathematics, and I never had a formal training in programming, in fact. Sometimes this shows up. But I am fortunate enough to be able to work in this small scale with some friends and technology people, some scientists. For example, now I am having fun with some friends that work in the subject of virtual reality, augmented reality, not only for entertainment, also for the industry. And now currently I'm working in a project with a cousin of mine who is a biologist, and he uses a small device to record the sounds of animals, in particular, in this case, bats. He's specialized in bats. And we are modifying the hardware, the software, the firmware that comes with this hardware, with this small hardware, to make the programming of the device more flexible, because my cousin needs this flexibility. The timing of the recording must adapt to the raising of the sun, etc., etc., etc. And this is really fun, but it's not Python, it's C. But I use Python for prototyping. Well, I have a scale for difficulty. The difficulty for this talk, not for you, not for the intended audience, but for me, while I was preparing the talk, it was more or less in the level of head scratching. Well, double head scratching. The hardest level is head folding. This is a joke because one of the sources that I used for this talk was the materials by David Beasley. And if you are a follower of David Beasley, probably you will know everything in this talk. And he makes jokes about the exploding heads when you are tackling with something difficult or deep or very convoluted. So the head exploding level here is a joke. If you are a Python guru like David Beasley, then you can tackle with this level of difficulty without your head exploding. Well, generators, Python generators. Here I did a joke with electricity generators, with electric generators. In fact, the concept of recursion, which is the other subject of this talk, has entered in the collective imagination and even in culture and entertainment. And there is some movies that play with the concept of recursion. One of them is from Christopher Nolan, who is also the creator of this other movie, The Prestige. This movie has many cool things. For example, rock star David Bowie playing a scientific genius, Nikola Tesla, in a Christopher Nolan movie, which is an accumulation of coolness from my point of view. Well, here we have Bowie playing Tesla and an electric generator. The idea is that an electric generator has a very simple principle, the friction, in fact. It uses friction to generate voltage, but it unleashes incredible power. And with the Python generators, something similar happens. They are very simple in concept, but they are very powerful. Well, we start with the easy things. A Python generator is similar to a function, but not exactly a function. It's a function that you can call one time, and then another time, and then another, and then another, and then another. You can call it recurrently. And then the values that it yields are updated according to the actions that you define in the function. It is function that it's not exactly a function. But it's a callable object, and it does not return an object of a certain type. It returns always an object of generator type. And it's relatively easy to turn a function into a generator by substituting return by yield, if it makes sense as a generator. And then you can generate, for example, numbers, the natural numbers, which is different from mathematician. And another attractive feature for me is that this is potentially infinite, and so the numbers may exceed the limits of this slide. A new step. I am going to use this number generator later. I have tried to make all the slides executable in theory, if I'm not mistaken. If you execute this result. Well, in Python 3, a cool feature was added that is called generator delegation. And I found it irresistible to illustrate this with this cool shot of The Prestige, again with David Bowie playing Tesla, where he delegates the power of generating, in this case, electricity, to the person who he is holding hands with. He's holding hands with one of the protagonists of the film. And then this other person receives the power to light this enormous light bulb. So, generator delegation. And this is a simple way to obtain values from a generator for another. And then, for example, if you create a generator, you can use the same syntax to obtain values, for example, from a list or an iterable, not only a generator, but with the same result as before. And at the end, I'm going to use this syntax, this give from, in a way that simplifies things. Well, the generators are more than just generators. Even before the addition of yield from in Python 3, already in Python 2, there was a possibility to send values to a generator, which I consider a kind of reverse yield. Generators not only yield values, they can receive them. So that this reverse yield, or the ability to receive values, gives to generators even more power. And then you can feed values to a generator and obtain them back. and this has interesting consequences. So generators are more than just generators, and they are considerably powerful. Well, now recursion, because my aim is to combine generators and recursion. And as I said, recursion has made its way into popular imagination, and in particular in cool movies like Inception by Christopher Nolan, again. And this image illustrates the concept of recursion with two mirrors that create an apparently infinite path to the ever far away horizon. Well, in this movie plays a lot with recursion, and I absolutely love it. Well, a typical example of recursion, perhaps one of the first that are explained when introducing recursion, is factorial. Other typical examples that you probably know are the Fibonacci sequence. For example, I had another example that I just forgot. It surely will pop again in my head. The factorial is the product of consecutive numbers, and then it's just only natural, especially for a mathematician, to define it in terms of a recurrence. If you have a recurrence, you can use recursion for the calculation. With the colors, I forgot to tell that, but when the color of the sequence is green, this means that we do not hit a recursion limit. Until now, we didn't have this problem because we had an introduced recursion. But if the colors, if the sequence is red, then we run the risk of hitting the recursion limit. In this case, we will hit the recursion limit if n is 1000, because the default recursion limit in Python is 1000. But we can change this recursion limit, as you probably know. And there are ways to avoid the recursion limit. And then you are only limited by the time of the calculation and the memory space. Well, this is easy for the factorial. It's obvious that it is the product of consecutive numbers, and you can calculate it in this way. But we're going to see alternatives and the application of generators, and then recursive generators. Well, if we step back from recursion and try to avoid it, another easy way to calculate the factorial is just as in the definition, as the product of consecutive numbers. With a simple loop, not exactly dynamic programming, or yes, it is dynamic programming because we're using values for future calculations, but it's a very simple case. There is a fun anecdote about the origin of the name dynamic programming, but I'm telling it for later. Well, in this case, we don't use recursion, so we don't fit the recursion limit. The numbers are linear. Well, can we use generators to calculate the factorial? Yes, in a similar way. We can turn that dynamic programming into a generator that will spew out successive factorials without hitting the recursion limit. But for a mathematician, it's cool to use recursion. So I would like to use a recursive generator to calculate the factorial without hitting the recursion limit. We can create a recursive generator to calculate the factorial. For this, I needed some head scratching, not double head scratching, but some head scratching. But finally, I ended up with this calculation, with this algorithm. And as you can see, the very function that we are defining calls itself, so there is recursion. And the risk of hitting the limit, so the numbers are red. Well, We can circumvent the recursion limit with some tricks. We can take advantage from Python features or simply apply conceptual tricks. This is another example of the of popular culture displaying recursion. This is a very well-known drawing by Escher, who used the recursion and other mathematical concepts in his works. And this is to illustrate that one of the problems of recursion, especially of mutual recursion. You have functions that, or generators, objects that call one another for whatever reasons. It's the fact that someone has to start. What is the starting point? In this famous Escher drawing, there is no starting point. Apparently, each hand creates the other, and there is no way to know what hand was first. We need to circumvent this kind of problems, but I'm starting not with the mutual recursion, but with the factorial. I wanted to calculate the factorial recursively, but with a generator, with a recursive generator, but without hitting the recursion limit. And there is a trick by Alex Bill, inspired probably by David Beasley, in a block entry that I love, that's called bouncing generator with a trampoline. There is a trampoline. And the trick that he applies is simple and fun, at least for me. In the previous version, I used the definition inside the function inside the definition of the function. So this was a recursive definition. This case is somewhat different. Of course, the function appears here in its very own definition. So we have recursion. But in this case, here we are yielding a generator. And this is Alex Bill's trick, to yield a generator. And then the trampoline, Alex Bill's trampoline, is in fact very simple. This is a function that will modify our generator. This could be a operator. And here the important part is that we repeat the step and obtain a new generator, and then a new generator, and then a new generator, until we reach the end of the recursion. And then in that case, the object is not a generator any longer. It's now a value, and then this value is returned. And with this trick, with the trampoline trick, and returning a generator instead of a value, except at the end, then you can obtain the factorials with a recursive generator without hitting the recursion limit. The numbers are green. In fact, here the sequence is just to show the factorial numbers, but you could calculate only one of them. Here there is a lot of repetition of calculations. But the calculation of a single value is, you could say, optimal. And here you can put a large number below, above the recursion limit, and there are no problems. You are limited only by the time and the space of memory, of course, but not by the recursion limit. We are not blowing up the stack. The stack is protected, so to speak. That's the idea. Well, Alex Bill, in his blog entry, recommends David Beasley, and I do too, but probably you know it already. Well,
Can you walk through to the previous example?
Yes. Yes. Here, the variables that I need for the calculation are displayed inside the arguments of the generator. So this is the same calculation that I had before, but it's here inside the argument. You increment the current value that initially is 1, you increment it, and you multiply for you multiply with an x that initially is 1. So you are multiplying 1, then by 2, times 3, times 4, times 5.
The trampoline help?
Sorry?
How does the trampoline help?
Yes, the trampoline is getting each time the new generator. So at the end, at the beginning, you have a generator for all the string of numbers. Then only for the second to the last. Then only for the first to last. And at the end, when you have reached the count 0, then you return the value that is stored in next, and has the cumulative effect of all the products. Of all the multiplications. That's why here we have G equals next G. And the trick is that next G is not a value, it's a generator. So the generator is regenerating itself until the final value is reached. That's the thing. And in this way, we can avoid hitting the recursion limit.
So the old generator gets refactored, gets cleaned up, and
yes, you create a new generator from the old one. Yes. But not unlike dynamic programming, in fact. But using this kind of trick, you may obtain perhaps a more precise expression. And I think the conciseness is useful and valuable. Well, if you want to use mutual recursion, there is also a way to circumvent the recursion problems. In this case, the problem that we visualize with the hands, with the Escher hands. Someone has to start. We cannot have a mutual calling since the beginning of time or since infinity. There must be a beginning, and there must be a starting point. Then one way to do it simple. This is my invention, but I just wanted to prepare things for the explanation of a trick by David Beasley. We can take advantage of this ability of generators to receive values. And when they do that, they are acting not only as generators, but also as coroutines in a certain way. And in this case, using this feature that was already introduced in Python 2, if we assign the yield to a variable, and then yield this variable with certain operation, then we can send a value to the generator to obtain the result of this operation. For example, here, to illustrate the interplay between two mutually calling functions or mutually calling generators, I use this simple operation: add 2 subtract 1, add 2 subtract 1, add 2 subtract 1. Then, in this case, we can avoid the starting point problem in a simple way. We create two objects of this type, an add 2 object and subtract 1 object, and a variable, an auxiliary variable with initial value there. Then, this generator coroutines objects must be primed with the first next to go to the queue. And then you can, once this is done, you can send messages to them with values and retrieve the result of the operation in a variable. And using these variables x and y in sequence, we can recursively and mutually manage the callings from one generator to the other without hitting the recursion limit either. Well, this is not very sophisticated because we have here this next, etc. And David Beasley is more sophisticated, and he circumvents the starting point problem in a really cool way. That is sophistication of what I have just explained. Well, this is the hardest slide in the talk. This and the two following. Well, he uses a double ending queue as a messaging queue, and a dictionary as registry of what is happening. To keep track of what's happening. But in general, simple. In the message queue, he stores the name of the generator to be called and the message that we send to it. And then he uses this function when needed. The main function is this run, that while there is something in the message queue, extracts the name and the message and sends the message to the object by name. We will have just two generators, one or the other. Then he defines a decorator that he calls actor, more or less to hide the ugly things that we had here, the need to prime the generator to begin with next, and the message sending. Message sending no. Well, the fact that we have to store the name somewhere. This is done here in the decorator. He obtains the generator, he primes the generator, and stores the name of the generator in the registry. And then we can use these names for the calling. And using the names in this way, we can avoid the starting point problem, because we can always call a function using its name. I mean that if you create the generators and you are defining them, and in the definition you have another generator, and the other generator calls the first one in the definition already, then you have a problem, because when you want to create the generator, the other is missing, and that's a starting point problem in mutual recursion. But using the names, we can avoid this problem. That's the cool trick by David Beasley. These are also is useful to avoid hitting the recursion limit. But we had solved this problem already. I think that the cool thing about the trick by David Beasley is avoiding the starting point problem of mutual recursion. Well, the two mutually calling generators are very simple. This is directly from David Beasley's example, ping pong. He uses this example in one of his talks. And we use what we already have seen. We store the yield in a variable. We print what this generator is doing. And we send the message to the other generator, increasing the value. And here is the key use of the name that avoids the problem of the starting point. The other generator is more or less the same, but it's the other side. Instead of ping, we have pong. Ping and pong are interchanged. And here, we just need to call ping and pong. We don't need to store anything because the actor, decorator, takes care of everything. Storing the name, priming the generator. And once this is done, we can start the mutual recursion, sending the first generator value, the starting value. We send 0 to ping and call prime. And the output is this. This may continue forever without ever hitting the recursion limit. So the numbers are green. And in this way we circumvent the starting point problem. And also the recursion limit problem. All the problem. Well, I cannot recommend enough everything that David Beasley has done or does. Well, a little more recursion. Here another popular example of recursion, the Matrixkers, the Russian dolls. This is very classical, very old, one of the oldest. Well, I'd like, as a mathematician, I would like to combine recursion and generators in other ways. For example, I can create a generator to obtain the sum of the numbers that another generator gives me, the successive sums. And then I can use another generator to create this generator. So this sum generator gives me the sums of the first n values of the given by another generator, and then you can increase n and obtain the sums. And this is something that we mathematicians do a lot. If I have a generator of ones, which is very simple and repetitive, but fun too, then you can use this generator to recursively, but using recursion in another way, in a different way, construct other generators. If I apply the sum generator once, I have the natural numbers, because I am adding 1, 1, 1, 1. If I add the successive natural numbers, I obtain the triangular numbers. So the double application of the sum generator gives me the triangular numbers. If I do this again, another time, then I obtain the sum of triangular numbers. This is constant, this is linear, this is quadratic, this is cubic, etc., etc., etc. If you pile triangles up, you have a pyramid. So this is volume, this is cubic. And here we have another kind of recursion. Here I recursively call sum generator, which starts as a useful starting point, and this allows the creation of many, many generators of mathematical interest, at least. So we can combine generators and recursion in another way, completely different of what we have seen before. Well, and there are contexts in which the application of recursion is natural and gives possibly the best solutions and the more concise ones. For example, if you want to obtain the permutations of a string, it is very natural to apply recursion, because if you separate one character, then you just need the permutations of the remaining string. And applying this idea, you can obtain permutations easily with recursion. In this case, the numbers are red, because here we don't avoid the recursion limit, but this doesn't bother me very much, because usually I don't need to permutate 1,000 characters And I could modify the recursion limit, or I could apply some of the tricks that we've seen before, or one different algorithm. But in any case, this perhaps is one of the more concise solutions to obtain permutations. Apart from the built-in Python function, of course, in the tools, I think, in the tools model, like the tools model. And another very natural place to apply recursion is in what is equivalent to tree traversal or tree exploring, because a nested list, a multiply nested list, is equivalent to a tree, and flattening the list to its elements is equivalent to enumerating the three nodes. And here, the yield from feature of Python really simplifies things and allows us to program the tree traversal in a really concise way. Just 3 or 4 lines. It's very easy. We just check if the tree is already flat. In that case, we use the node. Otherwise, we yield from the result of flattening the first element in the list. And if there are more elements, then we yield from the flattening of the rest of the elements. And that's all. And this seems very simple, but everything is very simple once it is done. So once solved, yes, it is very simple. And this is equivalent to tree traversal. And tree traversal, as you know, is absolutely fundamental for computer science. The recursion itself is tree traversal, so really recursion was a natural solution. And if we can traverse a tree, you can explore a tree and enumerate all its nodes. Then we also, well, I mean, if we can do that, we can do everything. If you manage to, if you can manage a tree, you can manage everything. Because after all, reality is hierarchical. Well, in this case, the numbers are red because we could hit the recursion limit. But if the tree is not very deep, we have no problems. And we could use the tricks that we have seen, or apply another algorithm. Okay. Well, and finally, something that is cool for a mathematician is that you can view generators as infinite sets. And the key is the lazy evaluation. The lazy evaluation, paradoxically, allows us to manage or handle infinite sets or potentially infinite sets, because you don't need to have all the sets at once. This is impossible because it is infinite. But if you can generate the values that you need as you need them, then you have potentially infinite set at your fingertips. And you can at least conceptually play with them and obtain the values from this set as you need them. Well, for example, if you have a list of numbers, then we can generate a list of its squares, of their squares. For example, with list comprehension, that is a very nice feature of Python. But we can have the generator version of this kind of generator comprehension. And if I use my natural number generator, here I have potentially the set of the squares of all natural numbers, which is an infinite set. And I have a generator for them. And I can play with this concise generator expression in Python, based on the parentheses, as the definition of a set. That is what I like as a mathematician. Here we have the definition of a finite set, of a set with a finite number of elements. But here we have the definition of an infinite set. And we can use them more extensively in an abstract way. For example, and even can use conditions on the elements of this set. And the computer doesn't explode, and my head doesn't explode either. I can select, for example, only the odd squares, for example. And I have a generator for them. I can eliminate an infinite number of terms, of even terms from the natural numbers at once. And the result is the set of square odd numbers. And well, as a mathematician, I very much like this possibility of generalizing this comprehension to infinite sets, thanks to generators, this kind of generator comprehension. And well, to end the talk, I will forgive my little joke here with the recursion.
But this is not valid Python.
Sorry?
This is not valid Python.
No,
I cannot run
this is LaTeX. Sorry, only. No, this is not valid Python. You cannot run this. I recommend again everything that David Beasley does in his talks. He has many materials in the web, video talks, and YouTube, etc. If you can take a look at Alex Bill blog entry, this is something I can recommend. And have fun. Have fun with generators, recursion, recursive generators, recursion applied to generators, generators that generate generators recursively, etc., etc., etc. The sky is the limit. And thank you.